Good morning, good
Yeah, now I'm recording.
Awesome. Thank you very much. Good morning, good afternoon, and good evening, everyone. Thanks for the introduction, Ahmed. I appreciate joining this talk and need to thank SBS student chapter, IADC, and University of North Dakota for providing me this opportunity to deliver this talk. Need to highlight that this presentation was prepared with the mindset that it's going to be educational purpose only. And today I'm going to talk about the far-field stress characterization for the geomechanical application, and which I found, based on my experience, the fundamental and critical aspect of geomechanic knowledge. By having this proper understanding of the far-field stress, we can achieve very good result and lead to successful operation. And failure, for sure, is going to be very costly, and NPT and so many difficulties through drilling and other operations, which I'm going to highlight through the presentation. And some topics may look simple for some of you, and appreciate your patience through those slides, since I tried to make the ground ready for all the audiences, and especially the university students. Let's dive into this topic. So I will start by providing an overview. What are the far-field stresses and what are the components of it, and where it is falling into the geomechanical modeling big picture. And then I will introduce different techniques to measure or estimate the far-field stresses, and the discussion will continue around the borehole and cavity stresses and relation to the far-field stress. I'm going to highlight slightly more around the borehole stresses and what are the relationship between the borehole stresses and the far-field stresses. And through the presentation, I will highlight the challenges and advantages and disadvantages of each method. And finally, I will try to close the talk by hearing from you and trying to answer your questions. So there are lots of operations in the oil and gas, geothermal, and geotechnical industries, which are relying heavily on the understanding of the far-field stress. For example, drilling is one of the activities. So to reach to the reservoir, which highly depend on the far-field stress information. Completion, if you want to define the, for example, completion tool and completion strategy, this is very critical, for example, to prevent sand production. Or if you want to do hydraulic fracturing, defining the far-field stresses and where to do the hydraulic fracturing and how to have an efficient hydraulic fracturing operation is highly dependent on the stress profile around the borehole and around the zone of interest. If we move to even to production, as we produce from the field, so there's going to be a depletion, and depletion going to change the pore pressure in the field, and pore pressure change going to consequently lead to changes into the lead to the changes into the far-field stresses. And I'm putting EOR and geothermal in one category. So because I can see the relation, and whatever knowledge we grasp through the EOR operation in the oil and gas industry, they are going to help us through the geothermal and even CCS, carbon capture and storage business. So basically, I can say that the knowledge is more or less same. We are injecting fluid to enhance the oil recovery, and in the geothermal, so more or less we are injecting fluid. So it could be hot fluid or cold fluid. The interaction between the fluid and the formation this is something critical knowledge to understand, and how the formation is going to react chemically and mechanically and and geochemically. So these are the things that needs to be considered when we are dealing with this operation. But still, far field stresses are very important. So you may question that where in the abandonment stage geomechanic and this knowledge going to help. So for sure, if we are if you want to abandon a well or abandon a field, so we are putting, for example, plugs, cement plugs, physical plugs, and these plugs need to stay intact in over the course of, for example, a decade. So, and we need to make sure that they are staying safe and they are not going to leak. And if there is a repressurization into the field, into the reservoir, this is not going to cause trouble such as caprock integrity problem. So these are the things that all relying heavily on proper characterizing the far field stresses. So need to highlight, I'm going to highlight that where this far field stress information is falling in the big picture. And the big picture, if you are talking to geomechanics engineers and specialists, they are talking about the mechanical earth model. Mechanical earth model, geomechanical earth model, GEM, MEM, these should be familiar to you guys. And it looks complicated. And to be honest, it is complicated. It's a big puzzle. It has several components. It has elastic, rock strength properties, pore pressure profile, stress profile. And these puzzle is trying to, basically what we are trying to do, we are trying to represent the far field in terms of and the formation in terms of those properties. And you cannot, it's same as the puzzle, you cannot force a piece of puzzle to the other piece location. Otherwise, the final product going to look ugly and it is not going to be usable. So you have to be careful, and there is a trick to it. Same as the puzzle. So you have to work with the simple and straightforward pieces. So for example, those who are on the corners, so you can easily guess those. For example, those corners in the MEM word, they can be overburden stress, elastic, somehow rock strength properties. They are more straightforward. And to be honest, the most complex one, which is sitting in the center, is far field stress. So to highlight the importance of far field stress, I'm going to give a quick review of the components of 1D MEM and the workflow to generate the 1D MEM. If you're familiar with the 1D MEM concept, is a formation representation, geomechanical formation representation around the borehole. So this is the basics and fundamentals of every geomechanical model. So we start by gathering lots of information. So because they are all can give us some idea about the formation, geomechanical formation properties, such as open hole log, resistivity information, image log, caliper data, direct pore pressure, surface map, seismic, end of well report, and DDR or drilling geological report. And we gather this data, we screen those data, and then as we finalized our candidate offset wells to be representative of the field that we are going to explore and we are going to further drill, for example, we are generating elastic and rock strength properties. I'm not going to elaborate what are the steps, but I'm going to highlight where the horizontal stress information is falling. And then we are going to mechanical stratigraphy, defining the mechanical stratigraphy column. So we need to know that what formation we are dealing and what are the characteristics of this formation. And then pore pressure profile, overburden stress, and later, close to our final product, we have horizontal stresses. And this is highlighting the fact that this piece of information is highly dependent on the rest of the steps that we already took to come up with this stage. And after that, by having the horizontal stress or product is, I can say, is ready, is not calibrated, is not tuned, but it is ready. It has all the properties. And then we do history matching and model validation, and to fine tune the model and come up with the calibrated and most representative model. Okay. So, but what are these far-field stresses? What is the definition? Where are they coming from? And I can say that any underground rock or sediment, they are subjected to a stresses. And in the geomechanic world, they are defined as, they are saying that three components of the stress tensor. So, and they are overburden, vertical stress, overburden, or minimum and maximum horizontal stress. And you can argue that they are not always vertical, they are not always horizontal, and that's true. They are not like that. So there could be rotation close to complex, for example, complex structures, which has been observed, for example. And this is not something that you can easily capture and model in the 1D mechanical earth modeling approach. This is requiring advanced modeling, but for time being, let's imagine that we are dealing with the overburden stress, which is vertical, and we have horizontal stresses. So I'm not saying that they are different, but let's call them minimum and maximum horizontal stress. So, and the easiest component of this tensor is the overburden stress. Basically, you can easily define it by having a density log, for example, density log, which is from, most of the time we have it in reservoir, and even in the overburden, we have the density log. If in some interval we don't have it, there are techniques to extrapolate the density, and then you have to add water and also consider the air gap interval to come up with the overburden gradient. And if you don't have access to density, which is quite rare, you can use some correlations such as Gardner to come up with the overburden gradient and overburden density in the PPG or equivalent domains, the SG or megapascal, which is a stress or pressure domain. So, and this is the formula that behind any of these calculations. So basically overburden is the integral of the density log. Combined and spliced density log. So overburden is easy, luckily. And we move to other stresses. What are the other sources of other stresses, horizontal stresses? Before diving deep into that concept, I need to explain what in the world of tectonic, they defined as a different stress regime. So based on the Andersonian tectonic classification, we have three tectonic stress regimes. So we have normal, thrust faulting, and struck and slip. There are different fault regimes. And basically in the geomechanic world and the Earth, we are dealing with these three scenarios. So it is not what we are dealing in terms of stresses, far-field stresses. It's not out of these three scenarios. Where is the good place to understand and learn about this is by checking the world stress map. This is the address. So you can go to this address and understand. It is very interesting. Even in my free time, I'm going to check that what is happening around the plates. So there are active plates, and then movement of the plates. They are correlating with the direction of the horizontal stresses and the stress regime. And the good thing is that you even have access to the data set itself. So you can download this data and you can use in your application. It is free and it is open source, as of my understanding. And it is a very valuable information to grasp. And it is going to, and another good thing is that there is a legend to this map, and it is highlighting where is the source of these information. Such a lots of these data are coming from the focal mechanism earthquake information, but even borehole information, very image log, caliper data based on these information are also leak of test information are also available, which is very handy. So for the location that you want to drill, I I strongly recommend that you check this website and get an overview and big picture of what is happening around your field and around your well and around your basically operation. So next, I'm going to highlight pore pressure. Maybe you question that why I'm bringing pore pressure, it is out of the topic. So there is a strong relation between the pore pressure and horizontal stress. I need to give a quick recap of what is the pore pressure and what is the relation to basically to far field stresses. So pore pressure is the fluid pressure between the grains of the rock. And based on the amount of pore pressure inside the space of the grain, space between the grain, we can have three scenarios in your field and your reservoir. So we can have overpressure zone, we can have under pressure, and we can have hydrostatic pressure or normal pore pressure. This is the simplest. Hydrostatic pore pressure is the simplest scenario. So basically it's the hydrostatic column of fluid. So which can be water, oil, or whatever. And then if there is a depletion, we are expecting under compaction, so less than the hydrostatic. And overpressure is something challenging, and it is interesting and needs to further get elaborated. So if overpressure happening, so based on the research that they did, they came up with the two scenarios. So they call them type 1 and type 2. Type 1 is, they classified them in two categories. Type 1, if their pore pressure, overpressure is related to porosity or it's not related to porosity. And one of the important, when there is a relation between porosity and pore pressure, it is, they call it under compaction as well. So whenever there is a rapid sedimentation and thick shell interval and low permeability and high compressibility rock, these are the components of creating overpressure under compaction. So basically the formation is not allowed to compact enough. So, and this is creating excessive pore pressure. And there are other sources of the overpressure which are not related to porosity, for example, shale uplift and source of fluid injection, for example. Whenever I'm looking at this one, it reminds me of a project that I was doing in East Asia. And I was having a hard time to understand that why my pore pressure doesn't match. Basically, I found that later that they were injecting in, and they were not sharing this piece of very important information with me. And I was trying to match my compaction trend line and so many things to get it match the actual measurement with my model, which was not possible without having the knowledge that there was a source of fluid, there was an injection happening into that reservoir. So we have to measure and or estimate the pore pressure. If there are several techniques to measure the direct measurements. So to direct measure the pore pressure, if it is a permeable zone, for example, sand, any quartz gauge, pressure transducer equipment such as MDT or XPT or equivalent in the other service companies, then Schlumberger, they are working. So in this media, and then in this type of scenario, and if it is impermeable zone, if it is shale, for example, still we can do a direct measurement, but it is not going to be very practical and efficient way. So because shale are very low in permeability, and it's going to take a long time, which still I have seen that maybe Total or Shell, they tried and they came up with the pore pressure in the shale, but it is not something that every operator want to try that. In contrast, we are trying to do indirect estimation of the pore pressure in the impermeable zone. And for the permeable zone, I will cover that one. But for the permeable formation, if it is sand, for example, indication of the overpressure, such as influx, connection gas, kick, for example, if you are drilling with the mud weight of, for example, 8 ppg and you are seeing kick, so you should at the depths of 2000 meter, for example. Sorry if my units are in the ppg or not everyone is familiar, but yeah, so you are getting the concept that I'm trying to convey here. So if you have the mud weight, if we know the mud weight, we know the pore pressure, we know the depth, so we should be able to back calculate the pore pressure if such an event such as influx or kick is happening. Impermeable, for example, shale, we are estimating. And this is very interesting. Why we are doing the shale estimate? Because drillers, this concept is coming through the air that drillers, I'm not saying that they are conservative people, but they don't like to get surprised. And it is absolutely makes sense because they are in the battlefield and it is very risky operation. They didn't want to get risk. They didn't want to get to risky operation, and they were urging geologists to come up with some estimation of the pore pressure in the permeable sand, which is right below the shale, thick shale, for example. And they were seeing that lots of time, this is the sand is overpressure and giving them trouble. This is why lots of people such as Eaton, Bowers, and other people, they try to come up with the estimation of the pore pressure. And they, to be honest, they did an awesome job. So the theory still is valid after so many years. And the technique is they try to establish the normal compaction and the measurements which are sensitive to the porosity. And when there is a deviation from the normal compaction, they are becoming suspicious that something is happening, and that something is really important one. So that under compaction is correlating to overpressure. You can see that overpressure here. And this is only valid in the shale interval. It is not for the sand, but the sand body, which is, for example, imagine that it is sitting here. It is a good assumption that they are in the equilibrium state with the adjacent formation, and they are taking, if there is no depletion or injection, they are going to have more or less same pore pressure. This was giving them early indication of what pore pressure they should anticipate in the upcoming permeable formation. So I guess we are clear on the pore pressure. We are moving back to our topic of interest, which are horizontal stress determination. So if there is no tectonic, so in the simple word, not simple word, it happens in the tectonic, in geotechnical word, that there is no horizontal tectonic. So, and very ideal situation that we generally in the geomechanic world, we are not dealing with that scenario. So we call it, this case, we are calling it uniaxial strain model. Basically, there is no lateral strain. And imagine that we have a cylinder of empty cylinder, and we are putting some sand into the cylinder. And at the bottom of the cylinder, so you should expect, since the sands, they are not allowed to move, there is going to be a generation of the stress. And so minimum and maximum horizontal stress, they are going to be same. There is no stress anisotropy, basically. But in the geomechanic world, you are drilling formation, there is a stress anisotropy. It can be very minor, but most of the time we are dealing with the formation that there is a tectonic and there is a stress anisotropy, and we need to come up with the different magnitude between the minimum and maximum horizontal stress. And I'm always saying that the oil is always in the complex environment. It is not easy to reach to the oil, and it is most of the time you are dealing with the harsh environments, and they are complex, geologically complex environments. So what are the source of information to understand the tectonic and get some idea about horizontal stresses, you can look at the geological information. So you can look at, for example, this anticline, and you can guess that the maximum stress direction should be in that direction. And then you can check the focal mechanism information, such as these are the earthquake information, and get an idea about the stress regime. But personally, I don't recommend. So they are a good indication of the big picture and giving you a good idea of general, but they can be misleading because they may not be representative of the current time of the current time of the your field or reservoir that you are going to operate. So they can be very old data, so which tectonic was active maybe million years ago, and something else is happening in your field and your reservoir. So this is why my recommendation, and every geomechanic expert recommendation, is looking at the borehole information. So you may question that why borehole? And because there is a good relation. They found that some people like Kirsch, they did a very extensive study, and they found that there is a good relation between the around the borehole stresses, which are not same as the far field. So we are naming them differently. They are hoop stress components of tangential stress, radial stress, and axial stress. And there is a good relation between these around the borehole stresses and far field stresses. So that's a good indication. That's a good starting point. If we can somehow get idea about the far field stresses, which we have access, so we can back calculate far field stresses. Good, because this is indicating the fact that by drilling a borehole, there is going to be a disturbance into the field. It is a column of rock that they did the experiment, so to realize that phenomenon. So to characterize the horizontal stresses, there are two major components there. So one of them is direction, which is easier than the magnitude, so which I'm going to cover first. So as mentioned on previous slide, so structural geology, focal mechanism, earthquake information, they can give us some idea about the stress direction, but may or may not be representative to the current stress state of the field or reservoir. But the most important and reliable data, they are coming from the wellbore. We know that we have access to image log, geological image log, for example, resistivity and density, and some indication of borehole deformation through these image logs can be a good indication of the far field stresses. Oriented caliper data, multi-arm caliper information, dipole sonic, and instrumented packers. So I'm highlighting dipole sonic and instrumented packer because I'm more fan of these two techniques. They are not depending on the borehole, already deformed borehole information, which can be misleading. I will highlight that in the upcoming slide. But let's focus here, the image log. So image log, how image log can be helpful. If we have breakout or induced fracture data, we know that the breakout in the vertical borehole or close to the vertical borehole, they are happening in the direction of minimum horizontal stress, and induced fracture happening in the direction of the maximum horizontal stress. So if we see these borehole features, we can correlate to the direction of the maximum and minimum horizontal stress. So this information about the borehole deformation, they can come from the caliper data or image log. But you should be very careful with this data because they can be easily misleading and they need to be properly screened. So this is from one of my paper that what I did, I screened the data and just highlighted the interval and picked the interval which I found that is representative of a breakout because there are other borehole features. So key seed, for example, washouts, they can be easily assumed to be breakout and induced fracture, but they are not. So this is why, and these are very prone to be affected by drilling activities. This is what I am personally, I try to be very careful with this information. But other information, dipole sonic is very good in that aspect. So we know that the dipole sonic has the capability of getting, it is in its own nature is polarized, it's getting polarized, and it is getting polarized to anisotropy, different type of anisotropy. I'm going to highlight on the upcoming slide, but as the dipole shear sonic getting polarized into the fast and the slow shear, so they found that the fast shear is traveling in the direction of the maximum horizontal stress, and the slow is traveling in the direction of the minimum horizontal stress. So getting this data from the dipole, proper dipole sonic tools, it can be a good indication of the what are the horizontal stress direction. And you don't need the borehole, failed borehole or damaged borehole, induced fracture. So it can be run in some certain formation, but basically it is independence of the borehole deformation. So the other component is magnitude of horizontal stresses. So what are the techniques to estimate or define the horizontal stresses? We can use Moore column friction model, so which is just defining the boundary. So you can say that, okay, your formation is failed or hasn't failed, and define the boundary accordingly by considering simple Moore column model with the friction model to come up with because this is also important. So we don't want just one point of information. So you may say that, okay, leak of test, and that's the which I'm going to elaborate further. So they are going to give a good indication, they are going to provide better indication of the horizontal magnitude of horizontal stress. That's true, but they are just one point, and we don't have continuous profile, which we want. So they can be used as a calibration data, but they're not providing the continuous profile. We need some equations, which are, for example, this is a proelastic equation. There is a minimum and maximum. I'm just showing here the minimum horizontal stress equation based on the proelastic equation, which is dependent on the Poisson ratio, overburden, pore pressure, Biot coefficient, and Young modulus, and these are the tectonic terms. So by using this equation and having access to this information, so you can come up with the profile, continuous, same as the compressional sonic log. So because you want to drill not only one interval of the borehole, you want to drill from surface to TD, and you need to have access to this information, continuous information, to define your safe mud window, for example, in the simplest application. And there are techniques around using the borehole breakout widths. And I know that this is very, very well established. I'm trying to be careful here. So this is a very well established equation and formula around this thing. And this technique, basically, they are trying to use borehole breakout widths and correlate it to the maximum horizontal stress, which is very good. I like the approach. However, this approach is the output can be compromised by some problems and some shortfalls. So if there is a time-dependent failure, for example, if there is a drilling activity, so which is causing that breakout, instead of showing 120 shows 140, what's going to happen? So this is why I have seen so many models out of this approach that they are overestimating the horizontal stresses. Um, Same as the other application around the breakout, it should be used by with lots of care. So you need to be very careful by utilizing this approach. And then you all familiar with the mini frag leak-off test and extended leak-off test. Basically, I'm highlighting here that I'm not going through leak-off test. So many people are expert on this. I'm a user of this. I have run this test and I know, but I prefer to don't spend too much around this thing. So there are different measurements that this is a proper test. This is the extended leak-off test. This is the arrangement that I like to do. So I like to frac the formation, let it close and reopen it at least in 2 cycles. And this is what I call it, personally, I call it extended leak-off test. And I believe that's going to provide the best information. So the information that we are interested in is fracture closure pressure, fracture propagation pressure. And this is what we are saying is corresponding to the minimum horizontal stress magnitude. And some people may argue that why leak-off test and FIT, for example, they are useless information. So in my point of view, they are not useless. They can be still used as some guidance to calibrate and validate the model if there is no proper information. So you should not disregard any information here. And then there is based on some formula around the tensile failure, which is happening at the time of formation breakdown. So you can use this formula, for example, to back calculate the maximum horizontal. This is not very popular approach to look at the maximum horizontal stress, but still, if this data is available, this is something that can be done. So this is the breakdown pressure, pore pressure, minimum and maximum and minimum horizontal stress, tensile strength, pore pressure, and bulk modulus. So by having this information, you can back calculate the maximum horizontal stress. This is what we are looking to find through this formula. Okay, and dipole sonic and instrumental packer. These are the things that I'm going to highlight in the next couple of slides. And as I mentioned, I have my own reason to give more weight to these approaches. So let's look at the dipole sonic. This is around this slide is around the sonic scanner and Schlumberger dipole sonic measurement. So basically, this is I'm a fan of this technique, to be honest, and I was promoting this technique, and I can see the value of this approach. So basically what they are trying to do is, we know that the dipole measurements getting polarized and getting, it has dispersive behavior, and it has the capability to, based on the different frequency, it has the capability to probe into the different depths to the formation. So these are the fundamentals around the dipole shear sonic measurement. So, and how it's getting polarized is whenever the dipole measures shear the sonic is seeing some anisotropy. It can be intrinsic anisotropy, for example, shale layers or fractures, or it can be stress-induced anisotropy. This is something that we in the world of geomechanics, so still, I'm not saying that we are not interested in this aspects of the measurement. So still understanding the TIV mode and for example, shale layer properties in terms of the rock mechanics is interesting. But in terms of characterizing the stresses, this is the place that we are interested. We are looking to see that what is the effect of stress anisotropy into the dipole measurements. So they did tons of experiment. They did lots of research, and they came up with the idea, with this concept that as the dipole measurement due to a stress getting polarized, they travel, it become two components instead of one. So it becomes fast and slow, and they travel into different direction. A fast shear is traveling in the direction of the maximum horizontal stress, and the slow shear is traveling in the direction of the minimum horizontal stress. So, okay, we know that there is a relation, but how this is more or less same as using it for the direction of the horizontal stress. How we can use this information to get the idea about magnitude, right? This is important. So it is very interesting what is happening here. So let's imagine that this is the direction of the maximum horizontal stress. This is the direction of the minimum horizontal stress. And there's going to be a breakout somehow at the direction of the minimum horizontal stress in this direction. So let's put the dipole measurement here, dipole sonic tool here, and let's run the measurements. So fast shear is traveling in the direction that there is the maximum stress concentration around the borehole, which is in the direction of the minimum. And as it gets far from the disturb zone, so it travels in the opposite direction. So it tries to rotate. Same is happening with the slow shear. And this is something that they have observed based on the measurement. They are seeing the crossover pattern. So between the fast and the slow shear. And they're trying to use this information. So this pattern, this measurements to back calculate the magnitude of minimum and maximum horizontal stress. So this is interesting, but what are the limitations? So this is based on my experience of promoting and using this product. So it is mathematically complex. So, and I'm not saying that this is well-established mathematical behind this thing, but people are not somehow getting sense of these measurements. So, and it requires lots of education. And also it is same as the other measurements. So, because we are converting sonic data to the stress data. So this conversion and the fact that it is the sonic measurements that are affected by the borehole fluid, for example. And then I know that there are some corrections to fix the measurements if there are different fluid characteristics to it. But I can say that it's a complex process and it is mathematically strong, but it has, and another fact is that it should be run in the sand, in the thick sand, which it cannot be run in the shale because shale has its own, they are trying to discriminate this, but still it's becoming more complex, basically, to be honest, to calculate it in the shale interval. So I have a paper, I highlighted the paper around this. So I published back in 2017, so you can read, and if you have any questions, so I would be more than happy to help. So,
sorry, I have
I have less time, right? So I have 2 more slides. Ahmed. Sorry, go ahead, please. Who is that?
Okay. Could you go back to the
previous slide?
Okay. Yes.
If you don't mind, I finished another 2 slides and I come back to Q&A session. If I'm so sorry. No please write down the slide number. It is number 12.
Okay, great.
Thank you.
Thank you.
You're welcome. So now I'm moving to another measurements that another technology that we are working here in the company that I'm working, the Integrity Institute. So we found that, as I mentioned, borehole, around the borehole, so whatever happening, there is a relation to the far field. So we found that, okay, so if we deform the borehole, so if we inflate the packer and then through the inflation and deflation, loading and unloading, we observed that how the instrumented, what I mean by instrumented, it has something like a calipers behind the packer. So if we can read the measurements and then back calculate, do some inversion to get access to what could be the stress anisotropy, this is I found it a smart technique, right? So this is, for example, what I'm doing here. So if you look at the video, what is happening? This is a packer. So I don't know what happened to my laser point. Yeah, let's see. This is a packer. I'm inflating. This is a finite element model. This is what I did in RS2 rock science finite element code. So I'm inflating the packer. That's the problem. So the laser point doesn't work with the animation. Okay. Bug reporting to Microsoft. So yeah, what you are seeing, this is the displacement on one point. So this is the measurements of the displacement. I picked one point here. Can you see my cursor? If anyone can.
Yes.
Awesome. So if we can capture the movement of that cell or that node, and then we compare the model against the actual measurements. So let's imagine that this is the solid line is the model finite element code, and the red dots are the measurements. So if we are seeing such a match, it's basically saying that the measurements and the assumptions of the stress anisotropy, elastic and rock strength properties, basically that puzzle that I presented at the first or second slide. So it is in the good shape, basically. So you may question that there are lots of components here. It is same. So it is same as the other. So other techniques. So you have to try to match those pieces of the puzzle to come up with the best representation. And basically there is another, sorry, there is, okay, I guess I missed that one. So the animation is masking this. This is another code. So for on the Itasca FLAC 2D. So these are the all finite element approach to look at this problem, to back calculate the mechanical properties, far field stresses, anisotropy, stress anisotropy. Yeah, this is, as I mentioned, this is an integrity in situ answer product. Intelligent packer becomes intelligent packer. Okay, so what is happening? So they are not, stresses are not fixed. So they may change through the course of field life, and that changes into the far field stresses can cause trouble. And trouble could be, for example, if we have the safe mode window here, and then there is a depleted zone. So you can imagine that there is no, you're not seeing any way to pass through this zone and reaching to the target. So basically there is a possibility that you are losing your safe mode window. This sort of thing can happen due to the depletion, due to the change of the stress profile. And rock properties alteration, for example, through the CCS or geothermal activities, they can lead to change into the stress profile. Heat, cold fluid injection, again, through the ER or CCS activities, they are again contributing to the change of the stresses. And the consequence could be fault reactivation, for example, subsidence, compaction, casing collapse. And there are ways to, we have to understand this thing. We cannot live with the, we cannot assume that the stresses are fixed. We have to model them, we have to characterize them, and we have to understand them. So there are approaches. 1D approach, if there is a, these are the two equations that I generally use in the 1D approach. They are around the kappa factor and then calculating the decrease or increase into the horizontal stresses. But my recommendation is always, if such a scenarios happen, is moving to the 3D stresses, because 3D geomechanical modeling using finite element engines to come up with the full field and representation of the stresses. So imagine that if there is a depletion here, for sure we know that this depletion is going to affect the adjacent layers, but this sort of thing in the 1D approach, they are basically overlooked, which can be very, very problematic at the time of drilling. My approach is because right now we have access to the good amount of CPU powers and also cloud processing. So my recommendation is always start from 1D, come up with the good understanding of, come up with the good understanding your field in the 1D domain and then move to 3D. And this is my last slide. Basically, what I'm trying to say that your model needs to be validated, and the best validation is checking against what was the experience. So this is screening the drilling events related to a stress profile, related to geomechanical model, tight hole, pack off, stockpile. These are the indication. If your model cannot reproduce those events, that experience on the offset well, your model is not representative and needs further calibration. You need to check to the caliper log. So for example, what is happening here, the mud weight is lower than the breakout. This is a safe mud window. And then we were expecting that there is a borehole breakout. And this is a synthetic image log. So it is showing some, for example, breakout, if you're familiar with the image log. And then you have to check, it is not the perfect match, I can say. But the good thing, for example, here is that the model managed to replicate the very complex failure model, so which is the high angle echelon. So it managed to reproduce that one. So which is giving a good indication that the model is representative and working. Fault reactivation, if these events are there, so there are indication that you need to validate your model based on these events: earthquake, casing collapse, caprock integrity, surface subsidence, sand production, for example, volume and rate. So this is a complex topic. I'm not going to touch that, but this information also can help to be used as a calibration parameters. And sorry if I rushed through the slides, so I realized that time is running. So thank you very much. And right now I'm ready for your questions.
Yeah, thank you so much, Dr. Babak, for the presentation. It was very informative. Yeah, it went through all the basics, going to the advanced topics.
I'm not a doctor, but
okay.
Thank you very much for that.
Well, yeah, we now can go to questions. So, dear audience, if you want to ask a question, feel free to unmute yourself and speak out. So we go with the first question from Olam. He was asking like earlier about slide 12, as I remember.
Okay, yeah. I'm going back to slide 12.
Then we move to Nima. As she raised your hand around,
Yeah.
Go ahead, Olam.
Slide 12. Go ahead, please.
Thank you, Ahmed. Thank you very much for this.
You're most welcome.
Presentation. I am already working on a project using sonic scanner to distinguish the open fractures from the closed fractures seen on the image log. My question is, what is the importance of the theoretical? There is a theoretical line that we have on the cross section of frequency with slowness. What is the importance of that curve to have it with the data, with the slow and the fast shear anisotropy curves?
That's a very good question. Thank you. So basically, your question is around this plot. So it is just a cartoon, but actual measurements should be looking more or less same thing, right? So what we are trying to do through this slowness frequency plot, so you can extract the maximum shear stress, and so by projecting that slowness frequency measurements along the borehole lengths, so borehole interval, you can come up with the fast shear, slow shear, and compressional, not compressional, sorry, and other measurements around the shear, which is Stoney, for example. So these sort of things can be understood based on the fast and the slow shear, but I'm not expert on the processing into the frequency and slowness measurement. But what I'm trying to imply here is that there is a relation between these measurements if there is a crossover pattern and the far field stresses. So there is another plot. There is a plot of radial profiling that it is on top of this plot, and basically they are translating the frequency and the depths of penetration to the actual depths. So they're plotting slowness versus depths, and that's a plot which they're using for the stress characterization and the stress calculation. But everything is around this measurement. So you are seeing this more often than the radial profiling.
Thank you very much for your answer.
You're most welcome. I hope I managed to answer your question. But anyhow, you can grab my contact and write me, and I hope that even if I cannot answer, so I may have a person to be able to help you on that.
Yeah, thank you, Ghulam, and thank you, Babak. Now we move to Nima. It was raising her hand or his hand. Rasaki.
No, I just wanted to thank you for the information you provided. Just thank you.
You're welcome.
Okay, so I have one question. Like the poroelastic theory have been always criticized for having a lot of uncertainty to use, and one of the leaders who have been doing that is Dr. Zobak. Yeah. So
I put the poroelasticity on top of the borehole deformation, the inversion. So I was expecting this sort of question can happen. Yes, you're right. So there are some uncertainty around the poroelasticity, but to my knowledge, is the best approach to come up with the continuous minimum and maximum horizontal stress. And there are EX and EY, there are other elastic and rock strength properties, but they are all dependent on each other, right? So you cannot focus on the Young modulus and elastic properties, for example, and disregard the relation to the maximum horizontal stress. They are all related. And for sure, if you are changing this one, there is a possibility that other one be problem. This is why, if you remember what I highlighted here, I like to go back to my third slide. Where's the slide? This is all piece of the puzzles.
yes.
So you have to solve the easy ones and then focus on the complex one. Yes, Young modulus, Poisson ratio, these are the simple ones. So if you are fixing these things, so using the poroelastic is less troublesome. But I'm saying that I'm also have seen the application around using the breakout width inversion, and I may use that approach as well.
I have another question. Like if we are trying to build the profile of pore pressure and we reach an overpressured zone, and then we get out from that overpressured zone, are we back to the hydrostatic or we are continuing from that overpressured zone?
Okay, so that's a good question. So let me go to my pore pressure slide. It depends. So if the good indication, so if you are started exploring that field, so most probably the only information you have are seismic data, right? Seismic velocity information.
Yes.
And this seismic data can give you indication. So I have seen that you are going with the worst case, low case, high case, optimum case. These are all around the uncertainty that people having. And the best guess for you is going to be building your model based on incorporating geology and understanding sand zone, for example, and possibility of the overpressure interconnection, for example, centroid effect and this sort of thing. I may like to have another presentation over the pore pressure. This is also an interesting topic.
Yes.
But yeah, there is a possibility that we go back to normal or even we stay over pressure, but the only information that we have in that case that you're highlighting, if we don't have the direct pore pressure data, is relying on the seismic. So, and the best guess is using the under compaction theory, for example. And if there is a sand body, so imagine the gradient, how much could be the gradient, and come up with the worst case scenario for your drilling operation.
Yes. Thank you very much.
You're welcome.
So do we have any other questions from the audience?
I'd like to say something, Bob Davis.
Sure.
Sure.
Kind of like to, excuse me, point it to the students. This was a really treat for you guys. This is the best talk I've heard on all the parameters you need to make a mechanical earth model I've ever
Many
seen.
thanks, Bob. Really appreciated your comment.
And it was so well explained. Even I understood it.
You are such a guru on this. So it's a pleasure having you on board, as I mentioned at the beginning.
I kind of was involved with putting this together in the early days of geomechanics with Schlumberger in 2000 or so. But it was good. The only thing I didn't hear you mention was hoop stress.
Oh, yeah. I mentioned the hoop stress. Maybe I was not loud enough. Yeah,
Maybe I was sleeping.
No, I'm pretty sure that I was not loud enough. Yeah, I said that hoop stresses, hoop stress around the borehole has three components: tangential, radial, and axial. And yeah, there is a relation as defined, for example, by Kirsch, the simplistic approach for the isotropic, hydrostat, and homogeneous formation developed by Kirsch. And there are more sophisticated approach that, for example, what I am using right now, it's finite element codes, but they are basically saying same thing, that there is a relation with borehole information and the far field.
Yeah, I saw the graphics that kind of explained it. I just missed the words, but
I'm so sorry.
Very hard thing for me to grasp was hoop stress. So
yeah, it's a hoop stress.
Yeah, we have.
Thank you very much.
Yeah, we have Wong. I think he wants to ask a question. He's raising his hand. Feel free to speak.
Okay, so first, thank you, sir, for a really nice presentation. So I just have a concern regarding, let's say if my purpose is I want to build a geomechanic model, but in the case that I don't really have a lot of data. So let's say, for example, I just have one report which is for that specific formation, and I just know the results from core data, and it's just two cores. And inside, I mean, the formation is obviously much more, thicker than just two cores there. So what is my best approach to
This is a very good question. If I pronounce your name Wong, right? Wong Pham?
Yes,
yeah, it is a very good question. So basically, geomechanic model is something dynamic, right? So you can, I'm telling my client, so that's the same as I'm talking to my client, that's the same argument. I'm saying that you can build a geomechanic model based on the gamma ray data. And you can invest heavily on the sonic scanner, on the instrumented packer, intelligent packer, or more advanced measurements. So to come up with more sophisticated model. So it depends on your application, but there is always something. So even I mentioned that word stress map, that can be a starting point for you. So it can be providing good information. So open source data. So there is a movement around the world that data becoming open, which is highly appreciated. So it's giving a good opportunity for people to learn, so to educate themselves. But yeah, I understand your concern. So, but seismic data can be used for building a rough model. And whenever there is a chance for adding more information from the offset data, offset well data, from the drilling experiences, all of this information should be gathered together to solve that puzzle. But you need the continuous for your approach, for your application. For example, your drilling, you need a continuous profile. And that continuous profile should be generated by some calculation based on the open hole log data or seismic data. You can use seismic velocity, use some correlation to calculate the shear sonic, shear velocity, and then having shear and velocity and the compressional velocity, you can calculate the other properties, Young modules, but still they are not going to be in the best quality. But, and the good thing that I'm hearing and I'm learning even further recently is using statistical information. So using a statistical approach, geostatistics. So these are the things that I'm not sure that it was giving enough weight and enough value. And this should be taught more in advance because everything here is around the data, and they are valuable data, and we need to give good weight and appreciate the data.
Okay.
I hope that managed to answer your question, but if I was not clear, please write me back. So I try to answer more in detail.
Yeah, thank you very much,
Thank you.
Ranham and Dr. Babak. I'm keeping saying doctor.
I have to get my doctor.
Yeah. Probably from the University of North Dakota.
To fix this thing.
Probably you can get it from the University of North Dakota. So Dr. Rasoli will take care of that. Yeah. So if we don't have any other questions.
Okay. Yeah, feel free to write to me. And whoever is getting access to this presentation in future, so through the recorded ones. So I left my contacts on the last slide, so for ease of getting access to me.
Thank you so much.
You are very welcome.
We just got a question.
Oh, you got
yeah. Is the actual geomechanics equation valid to understand thermally driven mechanical stress for geothermal application?
Okay. Yeah, I noticed that I didn't cover the geothermal in deep, but I thought that EOR operations, they are more or less same. So basically, geothermal coefficient, so thermal coefficient that we are using very general in every EOR operation. They are basically same. And if we are introducing thermal effect into the finite element codes, so which are able to handle that situation, that condition. So basically, I cannot see any difference between the EOR operation and geothermal. This is why I didn't go into detail into geothermal work. But yes, if there is a cooling effect or heating effect, so the rock stresses, rock properties can change. Even the rock stress can get altered through the injected wells, and that is going to influence the stresses. Yes.
Okay. So thank you, Omar, for your question, and thank you, Babak, for elaborating that.
You're most welcome.
Yeah. So since we don't have any other question, we would conclude our session. We just like to remind our attendees that our videos are posted on our YouTube channel. That would be the SPE University of North Dakota Student Chapter, and you will find a lot of educational content there. I would like to thank Babak Heidari for presenting about the far-field stress, and the audience for sticking till the end of this presentation. Thank you very much, everyone, and have a good day.
Have a good day. Thank you very much.
Thank you, Dr.
Thanks.
Babak, for the
Thank you.
presentation.
Cheers. Bye-bye.
Bye bye.
Bye.
Invitation.
Thank you. Wow. Really appreciate it.